Rust is not installed. Okay, if you don't have Rust compiler, all of those things set up, or if you are not on a somewhat recent nightly build, then you can go to the repo, look in the README, and we actually wrote instructions for how to update those things. So if you're getting non-repo related issues, go to the README of the repo, and then you'll see some update instructions. And that will take a long time. So you might want to sit next to someone who already has the build. Cool. I think we're going to go ahead and get started. Looks like we have a good collection of people. So hello, everyone. I'm Nicole.
I'm Amar.
Great. And we'll be battling the food coma with you guys over the next 2 hours.
So you have to as far from there as possible.
From there.
Yeah, that's why we pushed the tables up.
Oh, I see. Okay.
Okay. Yeah, that was.
Makes sense. We'll be implementing a end-to-end UTXO chain on Substrate. And we want to give a special shout out to Dimitri, who's really the mastermind behind this entire experiment. He couldn't be with us here today, but he's here with us in spirit. Oh yeah. Oh no, he's not dead. He's just in another city. That's not what we meant. Great. To get you excited, over the course of the workshop, you guys will learn how to implement the UTXO model on Substrate, which is out of the box a accounts-based model. How do we do that? You will secure your UTXO implementation against malicious transaction attacks. We'll show you how to configure your Genesis block and seed that with some initial UTXO, since in this ecosystem, we're not going to be mining coins from scratch. You'll learn how to reward block validators in this environment, in this non-POW environment. And last but not least, and you'll customize your transaction pool logic on Substrate. And hopefully, one other thing we can take away from this is some good coding patterns for working with Substrate and Rust. So this is our agenda. We're going to, of course, walk you guys through the boilerplate, which you get by going into the workshop branch. And as you can see, there are two challenges that we've teed up for you. One is the one where you kind of secure your implementation, and the other one is we'll look into a very interesting runtime API called tag transaction queue, and that'll let you encode some interesting logic on how to prioritize your transactions in the transaction pool and set dependencies for before the transaction executes. Great. And as a last reminder, if you're reading through the code in master, please don't. Cool. So why are we doing this? Why are we building UTXO on Substrate? So as a quick refresher for you guys, a lot of you know that UTXO versus accounts-based ledger keeping are the two most popular versions that we see out there. Substrate, if you played around with it, by default enables the accounts-based model. You guys might have seen the balances module, which gives accounts some numerical integer balance, and those accounts are authorized to spend those balances. UTXO, of course, is completely different. And we'll step into more of what that means in a short while. So we're doing this exercise because it demonstrates that you can implement a completely different ledger model on top of Substrate in a very, very fast and thorough way. And hopefully through this process, we can all evaluate and gain an appreciation for Substrate's flexibility. Great. So quick primer on UTXO. It is the foundation of the whole Bitcoin idea. It stands for unspent transaction inputs. And so in Bitcoin, each transaction spends outputs from prior transactions. And when it spends that, it generates a new output to be spent by a future transaction. So you don't have this notion of accounts and balances. You have a VEC or a set of unspent transactions that someone else might be authorized to spend again in the future. And all of these unspent transactions are kept in a fully synchronized node, and this model comprises of UTXO. And Bitcoin wallets, in turn, just keep track of a list of unspent transactions, which is a key phrase you'll see later in your implementation, and it just totals up these balances. And in the UI, that's how you see a balance associated with particular wallets. Cool. Quick refresher on the logic behind UTXO, and we'll shortly do a demo of our implementation that also simulates this. Great. So you're Bob. You own one unspent transaction output of 50 Bitcoins, and you want to give some money to Alice. You want to give her exactly 0.5 BTC. So in this ecosystem, Bob creates a transaction A, and for the input, he puts in his entire 50 BTC. And for his outputs, he pre-designates the 0.5 BTC that he wants to send to Alice, and a remainder amount that, of course, he wants to refund back to himself. Cool. So once this transaction is validated and it goes through, very obviously, Bob ends up with one UTXO of 49.5, and Alice has another one. So now 2 new UTXOs exist in the system, and the original one of 50 BTC no longer technically exists or is spendable. Cool. And so this forms a chain after many spends, right? These UTXOs are then spendable by future owners who can unlock future outputs. Cool. So under the hood, if you recall, this is what a traditional UTXO transaction looks like. So a single transaction has a list of inputs, a list of proofs, in most cases just the signatures allowing folks to spend those inputs, and a list of outputs that within its struct, within its object, also designate the next signature that's going to be required, or the next proof that's going to be required to unlock the UTXO. So to really rehash this point and how it's different from the account ledger model is that this mechanism is essentially just a continuous transgression of inputs and outputs, where you have the owner of the tokens who don't actually directly own the tokens, but rather they own the outputs to a specific number of tokens that can then be signed over as an input to a new owner who then controls the new outputs for subsequent transactions, and so on and so on. Cool. Last but not least, on the UTXO refresher part, there are 3 fundamental rules in this UTXO scheme. And you guys might want to make note of this, because it is a hint for your first exercise. Quite logically, every transaction must prove that the sum of its inputs are greater or equal to the sum of its outputs. Every referenced input must be valid and not yet spent. The transaction must have a signature matching the owner of the input for every output. Cool. If you guys want, take a quick photo, because you'll be implementing this in our UTXO implementation. Cool. All right. Any questions so far on the UTXO refresher? Oh, sorry. Workshop. Please be in the workshop branch. Don't peek at master. Great question, Joshi.
I didn't peek, but I did compile our own one.
Then you can follow along the demo if you've accidentally. Yeah.
Any other questions? All right.
Cool. If we're all good on UTXO logic, then let us move on to a demo. So by the end of the workshop, you'll have this up and running. So everything you see here, you'll be able to reproduce as well. And if you really want to skip ahead, the instructions for how to reproduce this demo and the pre-encoded hashes we've pre-generated for you are already there. Great. All right. Actually, I'm just going to mirror my 2 displays. Give us a second. Cool. I'm just purging some previous data. And I'm running a node in development mode. So I think when you guys reproduce this demo, you're going to have to do some initial setup, namely in settings. There's some previously encoded values like hash, signature, but we also designate some new ones, which we'll explain shortly. So in the UI, you just have to designate what it means. Otherwise, the console will give you a type not found error. OK, great. Can we see the steps? Slides. OK, sounds good. So what we've done so far is we have created this account called Nicole. In order for Nicole to send any extrinsics, let's first transfer her some balance. So Alex has been preceded with a lot of money. Let's have Alice give Nicole some balance. OK, great. So now that was an extrinsic success. So now we are all set up. OK, so what we want to demo here, and what you'll shortly see in the boilerplate, is with this implementation, we've seeded the initial Genesis block with one token, UTXO token allocation for this Nicole account of value, max value. So let's just go in and double check that that exists. So in chain state, we're going to go down, select the UTXO module, and we're going to look inside this UnspentOutputs vector. Do you remember how back in our UTXO discussion we mentioned that this essentially represents the total list of spendable yet unspent outputs? So we've pre-calculated the hash for where we've stored this transaction output that was generated on Genesis. And here we're able to verify that, yes, we do have one UTXO of max value that's assigned to this pub key, and that just happens to be my pub key of some, yeah. So if we change this to inspect something else, we haven't pre-generated it for this hash. Of course, it doesn't exist. Great. Oh, I see. Make this bigger? Oh, yeah, this is much better. OK, sorry. Are you guys able to see this now? So here we're just proving that we've preceded our blockchain with one UTXO. OK, so next we're going to have Nicole spend that UTXO. We're going to do quite an arbitrary transaction. So Nicole is going to spend, I think, 100 UTXO, or one UTXO of 100 value on herself. And then we're going to just discard the rest. We're going to burn the rest. Great. So inside extrinsics, let us select the Nicole account, check that she has some initial balance to send over extrinsics, select the UTXO model. So this execute function is sort of the main execute transaction function. And then inside here, it's expecting a encoded version of the transaction struct. And so I've just done that pre-encoding for you here. We're going to submit the inherent. Yeah. So that encoding decodes to this. This just says that this transaction consists of one input, the one that we just showed you guys in UnspentOutputs, that this signature, and in this case the signature belongs to Nicole, can spend this input. And in return, what we want to generate is I want to give one UTXO of value 100 back to my own public key. Cool. So that was successful. And I took a peek at the console, and it looks like it succeeded around block 26 or so. Let's just go to our blockchain explorer and double check that. So inside block details, let's just make a guess. Yeah, and here it is. So we see a successful transaction, our UTXO execute, which sent this one transaction. Great. And now we want to just double check that that transaction was successful. I want to check that Nicole, myself, I do now own another UTXO of value 100. And there it is. Cool. Yes, there is a question.
What's the hash? When you put a hash in there, that's like a transaction hash or a block hash, or what are you looking at?
Great question. We will step you through that in 3 minutes. Yeah. So by the end of the tutorial, you guys will know what all of these transactions mean and how we store our state. That's a great question. We will step through that in 3 minutes. Yeah. Go ahead.
So in the list of modules, I saw the indices module, which is basically the account module.
That's a really good question. It doesn't. So our implementation doesn't depend on that at all. In this demo, I used a boilerplate, which gives you indices, balances, modules out of the box. But our implementation actually doesn't depend on that at all. So what you can do is take a minute, remove all of those other module dependencies, and this will work still. All right, cool. So we'll be building that over the course of the next couple of hours. All right, cool. Last but not least, before we get started, the necessary disclaimer. The following implementation is not production ready. Use, modify, adopt at your own risk. And you'll notice just some important points to reemphasize. We don't support mining. We don't support Coinbase transactions in this instance. It'll be a fun extension for you to build and an interesting thought exercise. So here we just sort of handle UTXO transactions and we make sure that they're secured. Cool. If you haven't gone to the repo yet, here's another reminder. All right, cool.
Okay.
Yeah, so do you want to use the mic? We can just point it in.
I don't think they can read. Yeah, sure.
Yeah.
I don't think they can read the slide is what he said. Oh, yeah. Hello. Okay, so if you go to the utxo.rs file in the repo, and you go, I think it's like lines like 30 to 40, you'll see a few structs. So we're going to talk you through these basic structs that make up our transactions. So the first struct that we're going to go over is the transaction input struct. And for that struct, it has two fields, the parent output field, which references the UTXO to be spent. So that's a hash of the UTXO that we're spending. And then the signature, which verifies ownership of that UTXO. And that essentially verifies that the person who's submitting this input has the private key associated with the public key within that transaction output that's being claimed. Okay.
Are you guys able to follow along in your boilerplate? You're seeing the, okay, great.
Okay, yeah. You're in the utxo.rs file. Don't look at the screen. That's not going to help because it's not very readable. So in the utxo.rs file in the repo, I'm not controlling the screen. I think it's like lines 30 to 40. You'll see these structs that make up each transaction. So I just talked about the transaction input struct, and then we're discussing the transaction output struct. So that has three fields.
We should emphasize. So just to emphasize on why we've designed this transaction input struct, the parent output here is where we store the address of where this transaction input or where we point to the initial UTXO that we want to actually use as an input into the transaction. So an important distinction here is if you recall the UTXO struct that we showed you a little while ago, their parent output field actually comprises of the blockchain's transaction hash plus the index of where that UTXO is in that previous transaction. So this is the first fork in the road where our implementation differs from the traditional UTXO implementation. And the reason for that is we're implementing this in the runtime. So getting access to something like transaction hash, which is handled at the Substrate node level, requires some additional complex setup that we'll need to store maybe a mapping pointing to the transaction hashes. And that feels a little bit arbitrary in this context. Here, we can just create a mapping, as you can see later, and just store the pointers to the UTXO directly. And this also changes a couple of the security considerations, as you guys will see shortly.
Yes, and if we go to the transaction output struct, which should be below it, we'll see that it has 3 fields. So the first field is the value that is being held in this transaction output. The second field is that public key that was essentially referenced in the signature and transaction input. So the public key is associated with the output, and in order to spend the output, the owner has to provide the proof, which is that signature. And then we also use a salt value to ensure some level of uniqueness for each transaction output, and that's to distinguish it from others addressed to the same public key with the same value. So this prevents replay attacks in which someone who's watching the chain could copy the signature used in previous transaction inputs that claim the same value and public key. So the salt essentially adds uniqueness to every output. It's necessary for that reason.
Cool. Does that make sense so far? Any questions? Yes, following along? Great.
Okay. So this is the transaction struct, and it consists of the inputs, which is a vec of our transaction inputs, and then the outputs, which is also a vec of the transaction outputs. This is a helpful visualization for sort of seeing how a transaction would work, the inputs and the outputs. The value is actually a U128, so that's a typo, but otherwise everything up there is correct.
Yeah. So you'll be working with this later, so if you wanted to grab a quick photo and just use this as a cheat sheet and help visualize UTXO transactions in our implementation, grab a quick photo.
All right, so now we'll go through a quick transaction example with Alice and Bob. So these are 2 UTXOs. So Alice and Bob each have these UTXOs with different amounts, and we're going to talk about how they can use these UTXOs to form a transaction. So the first step is claiming their UTXOs. So that's where they're going to provide the inputs, and the parent field is the parent output field, which references the hash of the respective UTXOs. So for the top one, it references Alice, the UTXO associated with Alice, and the bottom one, it references the hash of the UTXO associated with Bob. And then the signature verifies the ownership of the private key associated with the public key in each of these UTXOs. Okay. And then this is the full transaction. So this adds the outputs, which indicates where they're sending the UTXOs. And the outputs, the sum of the outputs must be less than or equal to the sum of the inputs. So now if we look in our declare storage block, we're going to show how we store all of this in the runtime. So what we're talking about right now is the map between hash H256 and transaction outputs. It's called UnspentOutputs. And so this is the main state that is undergoing transition. And it essentially points the hashes of the UTXOs that can be spent to the actual outputs. And the build function within here is what we use to take the initial UTXO that we generate upon initialization and configure the map. So we're populating that with the hash of every transaction output that corresponds. Yeah. Okay. And because we don't support mining UTXOs, we want to precede our chain with our initial UTXOs. So we do that in chainspec.rs. And we set, so like here, if you can see the screen, we set the values equal to the maximum values, the public key as default 0, and the salt as 0, and all the other values are also set to be default.
Cool. Are you guys following along okay? Yes? Great. So if you remember from the demo, this is how we see the initial Genesis block with some tokens. Cool. No questions so far? Great. Great, we can move on to the part where we get hacking. So now that you guys have a good understanding of how we're handling UTXOs and some of the custom types that we've defined in our runtime, let's take a look at the last part that you need to know, which is the implementation. So if you scroll to the execute function, that's really the key to this whole UTXO logic. So quickly stepping you guys through what it's doing. It's accepting a, oh, there was a question. UTXO.rs. Yeah. Yep. So scroll down to the public execute function. It accepts a single transaction. And then there's this check here where it's ensure inherent. I think that this is getting deprecated. The new name for this function is going to be called ensure unsigned. So here it's just looking for a unsigned transaction, which is consistent to how Bitcoin transactions are sent. The transactions themselves are not signed, right? So then it checks the transaction validity. And this is the portion that you guys will be implementing, this check transaction function. If it receives a missing inputs type, as you guys can see, or if it returns a missing inputs type, it will error. And if it succeeds, it'll just generate this leftover value, which we'll talk about later, just take it at surface level, that simply calculates the total value of the inputs minus the total value of the outputs. So that comprises of your leftover. And finally, if and when the transaction is valid, it'll update the transaction by updating the storage. So you guys will read through this yourself, and very clearly inside update storage, if you guys can index down to that function, it's as you guys would expect. It clears unspent outputs. It clears the input UTXOs that are used, and it creates the new UTXOs that are generated from this successful transaction. Cool. Any questions so far? The boilerplate is really straightforward, but we wanted to step you guys through it in case there are any outstanding questions. We're good? Sweet. Moving on. Cool. The last thing to note is that is a good, I think, coding practice. We have this Checkinfo enum. This represents a critical fork in our runtime logic. Are you guys indexed down to the Checkinfo enum? Okay, great. So inside Checkinfo, there are two types. You can either return totals upon transaction success, or you can return this vector called missing inputs. So in our runtime logic, if you send in a transaction and it goes through all of the validations, and the only issue is that it's missing some inputs, we actually don't count that as an error. And we'll see more about what this means later. It has to do with network latencies and having transactions depend on other impending transactions. So for now, just take it for what it is, and note that your check transaction function should return this Checkinfo enum. Cool. Yeah, so right now, just make sure to handle missing inputs in your implementation. So given this context, and given the boilerplate that you guys have in front of you, you are ready for your first challenge. And here's another hint from UTXO implementation, although in our implementation, it'll vary slightly. Great. Cool. So the challenge is UTXO.rs, if you scroll all the way to the bottom of the file, there are a couple of tests, they're unit tests that simulate malicious transaction attacks. And each of the tests are quite unique, and they kind of attack a vector, and the different attack vectors don't really overlap. So your challenge here is to extend the implementation, the check validation function, such that the only secure transactions will go through. And for this, we also remind you guys to remember the check before changing the state, changing writing to storage pattern that we advise for all Substrate modules. Cool, yeah, so this is the first challenge. Are you guys able to run the test, and are you able to see all of the tests that are failing? Cool. This might take a while. I think at this point we can make the workshop a bit more unstructured. There are a couple of slides later on where we talk about other topics. But for now, I think for the next 30 minutes, so until 2:30, we can work on this implementation and work on the first challenge together. So if you're busy and you're not interested in doing the implementation, just make sure to come back at 2:30. All right, cool. In the meantime, we'll be here to help you with your implementation. And then maybe in the last 10 minutes, we'll step through the implementation step by step. But we're hoping that this could be, fun for you guys and you come up with the solutions yourselves.
The 1 pass and 7 failures, that's expected?
That is expected, correct. If you want another hint, the README and the repo suggests the correct sequence in which you should make the tests pass. All right, cool. I think we're going to float around. Feel free to sit next to someone and pair program. I'll play some music up here. Let us know if you have any questions. And come back at 2:30 if you want to hear the rest of this workshop. I'll show you. There's an error. Okay, 1 second. So you should get a bunch of warnings and then have 1 passed test and 7 failed tests. And I would run this command at the root of the directory. Hello. Oh, it's okay. I can just yell. All right, cool. I think we're going to regroup and walk through the implementation and emphasize a couple of the checks and why they were really significant. How many of you guys got through all of the tests? Nice. Whoa, impressivo. Half of the tests? Nice. Well, we didn't give you guys enough time. I'm sure with time you would have finished it all. One test? Cool, fantastic. Very nice. Great. I'm going to do my best to explain the implementation while glancing over my shoulder. So in the last half hour, you guys have really implemented the crux of the check validation logic. One of the first things that we check for is that inputs and outputs cannot be empty. Someone in the audience raised the point that, well, outputs could be empty. You're just sending transactions to burn your UTXO. That's fine. But in this case, we can also use it as a design decision that we don't want transactions to contain completely empty outputs. Cool. So the next check that we implemented, using this B tree map that we get from our crate, we dedupe all of our inputs in this map, and we just count how many unique input UTXOs are left over, and we compare it to the original transaction inputs vec, and we just check that there were no duplicate inputs. This is important, hence you should not be able to double spend. You should not be able to count duplicate inputs and be able to generate a sum that is greater than the inputs. Cool. After that, we do a very important check here. We iterate over all of the inputs, and we verify that the message, which in this case is the hash of the UTXO that you want to spend, was correctly signed, and the signature corresponds to the public key of the original person that was authorized to spend that unspent output.
Tell us more about like lines 204 and 205. I wasn't sure how to get an actual given an input, how do you get the output?
204 and 205. This is Rust shorthand. So unspent outputs, when you do get on unspent outputs, I think it returns an option of either some output or it returns none. And so this is Rust shorthand that just says if the result of what you get from this, if it matches some output, meaning some output exists in unspent outputs, then execute this condition.
Also, this corresponds to the unspent outputs map in storage between hashes and unspent outputs.
Oh, makes sense. Cool. Any questions so far? Great. And of course, if the input doesn't exist, we mentioned earlier, we actually don't want to panic right here and just kill everything. We want to handle this asynchronous race condition that some transactions can get to your pool before the other preceding transactions that it's dependent on make it there. So the way that you indicate what is missing is you create a missing UTXO vec, and you push the address, the hash of the UTXOs that are missing in order for this transaction to be valid. Cool. And last but not least, we iterate over the transaction outputs. We just check that the output values must be non-zero, prevent people from arbitrarily burning UTXOs. We want to prevent a potential output hash collision. We don't want to overwrite any existing value in the system. Let's see. And of course, this is a very important check. We're just checking that the output value is not exceeding input value. Yeah, pretty straightforward. If you guys don't have this implemented yet in your exercise, feel free to go over to master and copy over the implementation, run your tests through, and all of it should be passing. Are we good so far? Yeah. Oh, question?
So, since there is a missing input, does that mean that the user has to rewrite, or how does it get handled?
Oh, sorry, can you repeat your question?
So, with the missing input,
Yeah.
so how does it? So since there's a missing input and you just indicate that there's a missing input, so how does it get handled? Like, does the user have to retry the entire transaction? Or
That's a great question. That's one way it can be handled. We think that this implementation, or we're going to walk you through a alternative implementation that handles it in a slightly different way. So we're going to talk about your question next. Yeah, that's your second exercise.
Why do you? Does it work? Why do you check that total input is at least total output only in case of missing UTXO?
What?
Is empty?
Which line?
This line that is selected now. Why is it in the if and not outside of if?
Okay. So remember, from this check transaction function, it can return two different outcomes. One outcome is that the transaction passes all the checks, and that it can be processed or it can be updated in storage. The other outcome is that this transaction could be valid, but at the moment it is missing some inputs. Right.
It's not valid, even though we can miss it.
Sorry? Yeah, so one option is to just panic upon every transaction that somehow arrives in the transaction pool before the other transactions that it's dependent on. But in this case, we don't want to panic straight away, and we want to handle that asynchronous condition. So we're going to talk about that in about 5 minutes, if you can just hold on to your very good questions.
I have a really short question. At the top of the file just now, there's a SR25519 verify function. In the ensure statements,
Yes.
I was wondering which crate that comes from, or which module, because I don't see it anywhere.
I think it comes from SRIO. We can check. Yeah, there it is. And we actually import it up here, I think. Yeah, right here. Cool. All right, great. So the last piece to keep in mind as we move forward to transaction ordering is that these are your two returns. If the missing UTXO vec is empty, meaning your transaction has everything it needs in order to be written to state, then you return this totals value that contains the total input and the total output. And if you guys remember in the execute function, this is just used to compute some leftover value. In BTC, I think it's called dust. In this case, we just call it some leftover value that then gets distributed among your block authorities as some kind of an incentive mechanism. Cool. And if it is missing inputs, we're not panicking, we're not airing out, we're returning this missing inputs with a vector of the hash, the addresses of the UTXOs that are deemed missing for this transaction. Cool. Are you good so far? Following along? All right, great. Moving on. Cool. And again, if you haven't finished your implementation, you can take a peek in master and copy over the solution. Cool. So you guys have successfully performed all of these checks. Great. We wanted to emphasize two last pieces that you sort of get out of the box in your boilerplate. You guys have already encountered this, but if you can just step to the part where we declare a leftover value in declare storage. This is just a value that we're updating per block of all of the dust, of all of the leftover values that were not turned into a unspent transaction. And in this case, if you scroll further down, I think there's a function called spend leftover. It just spends this leftover. At the end of every block, it evenly distributes this leftover amount to all of your block authorities as a nice reward incentive mechanism in this ecosystem. Cool. And last but not least, we wanted to also highlight a quick extension that we built here, which is UTXO locking. This is interesting because Bitcoin nodes process transactions, and because they don't share the same state DB, it is hard to get a sense of which coins are locked and which ones are not. Similarly, I'm aware that in the Ethereum ecosystem, it's hard to check. You have to know exactly where to look to check for potential token locking logic. Right. So in this case, because we're using the same state, you can easily, within a couple of lines, implement this entire extension where you can have a locking mechanism on top of your UTXO coins. So we thought that was something that's very interesting to highlight. Cool. For the sake of time, I think we can move on to the last challenge. You guys are already 80% of the way through implementing your entire UTXO chain. So let's hang in there for the last couple of minutes. Cool.
So now we're actually going to expand on the race condition that Nicole mentioned like 5 minutes ago. So the basic situation is that imagine if, and I'll just use names to make it clear, but imagine if Bob sends Alice some funds, and then Alice uses those funds to send funds to Charlie. So Alice's transaction is dependent upon Bob's transaction. The second transaction is dependent on the first transaction. Because there could be network latency, we could run into this asynchronous race condition where the second transaction arrives before the first transaction. And one way to deal with that, a very naive solution, would be simply to drop the second transaction. But we know that we don't want to do that. So Substrate actually allows you to implement transaction ordering logic in a much cleaner way. So your second challenge will be to overcome this race condition by implementing that transaction ordering logic. And now we're going to go over two important implementation hints. So this is the trait that you'll be working with. It's called the tag transaction queue trait, and it helps us specify our transaction logic and prevent these race conditions. So to implement this trait, we have to fill in the logic for validate transaction, this function, and we need to consider how to verify transactions as well as the necessary steps to enforce consistent ordering. So let's see the second tip, I guess, or hint. Oh, that would be better. Okay, yeah, the docs are under challenge 2, actually on the README. There are references to the docs links to the tag transaction queue trait, as well as the transaction validity enum, which is returned in the case of successful execution of this function. So if you go to the README challenge 2, you'll find both of these. So the transaction validity enum is also important to sort of understand when we're doing this transaction ordering implementation. So when a transaction comes into the transaction pool, the transaction pool only allows the valid transactions to be executed. So this allows us to basically set some preconditions under which the valid transactions would be executed or discarded from the transaction pool. So if you can see, so the important things are the fields of valid. So we have priority, which determines the ordering of 2 transactions that have all their dependencies or required tags. And you guys can read about it. I'll say it anyway. So requires essentially tells us what transactions need to be included before the one in question, and then provides tell us what the dependent transactions, the transactions dependent upon these transactions are. And the longevity describes how long we wait until we remove the transaction from the pool. So with that, we're going to, I guess the next slide. So when you're trying to implement the transaction ordering logic, and this might be a little bit more confusing, but the questions you should sort of think about is within that transaction validity enum, what are you going to use as the require tag for a transaction in the context of UTXO? And then also what to do under these 3 scenarios. So as a hint, you'll set up like a match statement or something to sort of deal with these scenarios, missing inputs, an error, and also whether or not, like if the transaction is valid. So I think with that, yeah.
Yeah, so for this exercise, please refer to the documentation. Otherwise, it's really hard to know what's happening. And again, we'll go through the implementation here as well if you want to follow along. But there are two critical questions to think about before you start implementing your transaction ordering logic. One is, as Amar just mentioned, valid transactions have this require tag. That basically means when a transaction, say it comes from RPC, it gets into the transaction pool, at that point in time, it's going to wait until this require tag is fulfilled by another transaction that's provided the same tag in its provides field. So every transaction could require some stuff, and it could provide some stuff. So that's how we implement the logic behind these interdependencies, right? So in this scenario, given what you guys have implemented so far, what do you think we should use as the require tags for pending transactions that are missing other transaction inputs and that are missing the transactions that it's dependent on? What should we use as the tags? The hash of the UTXO. Correct, exactly. That's exactly the hint. So think about that and think about what your check transaction function returned, which is a vector of missing inputs, right, of all of the missing hashes. Yeah. Yep. And we've kind of structured the layout of the implementation here. Do you want to
go through the implementation? Okay, yeah. So we're dealing with these three scenarios. So we're checking if a transaction has missing outputs. And so within our match statement that we're going to have in the implementation, which I'll go through in a few minutes after you guys try and do this, we're going to have missing outputs. And in that case, we're probably going to want to collect those missing outputs. And then we're also dealing with the case of an error, which is like quite easy. Yeah, and then the last situation is if the transaction is valid. So.
All right. So to follow along, if you go inside your lib.rs file, that's going to be the template for your next challenge. We've set up this function here called validate transaction. Yeah, which uses the runtime API, this tag transaction queue. And then inside here, we have some hints for you on how to implement this next piece of logic. Before we get started, do you guys have any questions? So the first step is to go to the README and then go check out the reference docs to see how we've specified this runtime API. And then taking the hint that you want your tags to be the H256 token, UTXO token hashes. How might you implement this transaction pool ordering logic in your lib.rs file? There's no test for this one. Yeah, the test for this one is just if you run the demo. We don't have any integration.
Yeah.
I can hold the mic for you while you talk.
I'll show the code to just read it so I don't get things wrong. Okay. Yeah, this is it. Okay.
So implement it and then talk about it.
On this computer, switch spots. Is this on? Yeah. Okay. So. Oh, jeez, I can't. Can I mirror the screen or?
Yeah, you can mirror.
so slow, such a slow typer. It's fine.
Yeah.
Okay, so I guess first we're going to start out within this if-let statement. So this is this essentially allows us to do some special handling for the extrinsics that represent UTXO transactions. So we'll start. Could you hold this? Okay. So we'll start by declaring our requires tags, and then also declaring the priority, which will be the transaction priority that we assign. And then we're also going to have a error message or error code for the case of if transaction validity, the enum is invalid. So now we're going to go use our match statement that I talked about earlier, where I'm not used to your keyboard. Runtime.
Are you typing in the right place?
Oh, something just happened. No, you're right. Shoot. Okay, thanks. Requires. Okay. And the match statements here. And I don't want to type all this. Taking in the transaction. Yeah, I think so. That's good. So we deal with errors. We deal with the condition of a valid transaction too. We deal with missing inputs. Okay. Oh, wait. Okay.
I think you're missing an angle bracket after the runtime, I guess.
Line 300.
Oh, yeah.
Oh, here. Yeah, yeah. Okay. Yeah.
Cool. So I think Amar has just given you guys a hint on the structure of the solution. There's some new syntax and some new things here in how we set it up that might look strange. All you need to know is that for line 292 or 293, all that does is match a particular type of transaction. So inside the call enum, it just matches for exactly the execute function. Which is supposed to send the UTXO transaction. So only in this condition, only for execute function calls, do we then execute the following logic. So the other thing that you've set up in the template to pay attention to is here we're again calling into the check transaction function and depending on the results. So remember the function you guys just implemented. In some scenarios, you return an error. Right? So if the result from check transaction on an impeding transaction is an error, what do you do in that case? And then in the second case, if the transaction is checked and it's actually a valid transaction with all of the available inputs, what do you do in that case? And the hint is you want to dispatch the transaction. And then in the third scenario, when your transaction is missing inputs, how do you handle that? How do you make use of transaction validity? And how do you configure the provides and requires tags so that you know when it is okay to execute your transaction?
Is if-let, how does if-let work?
Yeah, so if-let is a shorthand for match statement. So typically, if you're expecting like an option to return, you would do like match. It's
I'm
better.
familiar with match and
Oh,
with like options, but I just didn't, so like,
So if-let just is shorthand for expecting one condition.
oh,
Yeah. I was confused by the,
so like,
because
okay.
reading it out loud, it doesn't really make sense, right?
Yeah.
If-let just
So
says,
we're-
if it is this condition, then do
Yeah,
that.
so let isn't like actually binding some new variable or anything, it's just like saying, it's like basically
If-let
like
the
saying-
outcome be
Yeah.
some output. And then
Okay.
this is also nice. It's a nice shorthand because then you can do if-else, right? Where
Oh.
else is like every other
Oh, like all the
condition.
other cases.
Yeah, yeah, all
Okay.
the other
So
cases.
it's basically like matching when you only want to match like there's one case that you want to match on, and then the
Yeah,
else would
exactly.
be like if it's any other
If
case.
let, yeah, the match result match this one case.
Okay, cool. So like in this example, oh, that's when you were talking about the execute function. Okay, thank you. I get
Yeah.
it.
Cool.
There's just two. Missing one? I think I have two. Really?
3 to 6, there should be another curly brace.
Here.
No. 4
3, 2, 6. Here. Oh. Yes. Okay.
Yeah, exactly.
I think there's too many here now. Pretty sure this is it. No, I think there's the right amount. I think I added two. Let me check. Does this correspond to that? Yeah, so that's right. And then the end of the function. So, or if that actually needs one. Sorry, if that needs one. Yeah. This is it. Should I talk through it now? Okay, so now I'm going to talk through the correct implementation. And so we're starting out within this if-let statement. and we're declaring our requires vector and priority, and we're going to assign that within the match statement, and then we're also defining this error code in the event of an invalid transaction. This is kind of... Okay, so within the match statement, we talked about how there are three different sort of ways, conditional paths this could go through. So the first one is error, and in that case, we're going to print the error and also return the invalid variant of the transaction validity enum with the error code that we assigned. The second conditional path would be the valid transaction, and in that case, we can just set requires equal to an empty vec because we know that the transaction is valid, so we don't need to put anything there. And then for priority, this might be a little bit confusing, but basically what we're doing is we're assigning it the priority. So we're assigning it the priority according to the difference between inputs and outputs, which is sort of like the transaction fee in this situation. And then we're just checking that that's less than the maximum possible priority that could be placed according to like the tag transaction queue trait. So
we thought that was a pretty clever implementation because you're essentially, so input minus output, if you guys recall, is leftover value. And leftover value is what gets distributed among the authorities. So here we're just saying we also want to use leftover value. And depending on if you leave more of an leftover value in your transaction, that transaction will get prioritized above others.
Yep. And then the last conditional path is if it's missing inputs, then you would place the missing ones in requires, and then the priority would be equal to 0 because it can't be validated because it's missing those transactions. And then the final thing that we do is we set provides equal to our transaction outputs, and then we return the transaction validity enum with the valid variant with each of our fields for that enum. And we set transaction longevity to the max value, so it's going to stay in our transaction pool for as long as that max value is. But one of the extensions would be changing this value and maybe setting it according to some other state-based condition. That's it. Yeah. I think that's basically it. And for non-UTXO transactions, this function would be used instead, which is from the executive SRML module. So that is how you deal with transaction ordering for the UTXO chain. Yeah. What's this? Okay.
Cool. Do you guys have any questions on the implementation? I know we rushed through that last part really quickly because we're coming up on the end of the workshop. Do you have any questions on using the runtime API for tag transaction queues and how to set your tags for requires, provides? Any questions? Oh, go ahead.
Are you aware of any projects actually implementing these models on either testnets, or are there any intentions for projects to apply these models, the UTXO model, as far as you know?
That's a really good question. Not to my knowledge, but I think this audience is a good collective of folks who would know the answer to that. Are you guys aware of any projects that are very similar to this? That's building on Substrate? Well, we hope that after this workshop, there could be. You guys have seen now just how easy and straightforward that is. Even in the short span of our workshop, we're able to get through the entire implementation. So please experiment with it. Please try it out and check out these potential extensions. They're just a couple of lines. And one of the interesting things to implement, as Amar just mentioned, is the idea of a smarter transaction longevity. Right now, it's just set to a max U256 value, which means bad transactions will sit around in your transaction pool forever. Maybe there's a way, maybe depending on the leftover amount that person specified, that you can come up with a smarter transaction longevity. So these are our recommended extensions. We hope that you do continue to play around with this. We hope that you run the short commands we have in the repo and you get your own demo on Substrate UI up and running. We hope that this was a good workshop for you guys.
Yeah, thanks, everyone. Also, just one last thing. So to sort of tangentially answer your question, the value proposition of using the UTXO model, so like one of the value adds would be transaction aggregation is actually more efficient with this model. So if you guys also, it would also help with respect to privacy. So if you guys have heard of Mimblewimble, they use they use the UTXO model to basically aggregate all the transactions, and then you keep the proof of like correct aggregation in each block instead of all the transactions. So no one except for the miners can see all of the transactions. So like that's an example of a application, I guess. Yeah, extension. Okay, thanks.